You think you know the triangle, right? It's simple, strong, a basic building block of, well, everything. But what if I told you that hidden inside this everyday shape are secret centers, points of perfect balance and symmetry? Let's dive in and find them. We're going to go on a little geometric quest, a hunt, really, to find not just one, but two of these special points. And what's wild is that you find each one using a totally different method, and they each have their own kind of magical property. So where do we even begin our search? Okay, so our journey starts with a very particular type of triangle. This one holds the first big clue we need. I'm talking about the isosceles triangle. Seriously, understanding this one is the key that unlocks this whole mystery. So what is an isosceles triangle? Well, it's pretty straightforward. It's a triangle with two sides that are the exact same length. We call those the legs. The angle between them, that's the vertex angle. The side opposite that is the base, and the two angles down at the bottom, those are your base angles. Easy enough, right? But trust me, the properties of this triangle, that's where things get really interesting. All right, check this out. An isosceles triangle has two superpowers, basically. First, those two base angles, they're always equal. Cool. But the second one, this is our golden ticket. If you draw a line that slices that top vertex angle perfectly in half, that line does something amazing. It hits the base at a perfect 90-degree angle, and it cuts the base into two perfectly equal pieces. Get that phrase in your head, perpendicular bisector. You're going to hear that again. Okay, before we jump into the hunt, we need to gear up. We need our tools. And in the world of geometry, our tools are proofs. We specifically need a way to prove that two right triangles are basically identical twins. The technical term is congruent. This is our toolkit, you know? It's how we'll confirm that the centers we find are the real deal. So here are the two big ones we'll be using just for right triangles. First up is RHA. That's for right angle, hypotenuse, angle. All it means is that if two right triangles have the same length hypotenuse and one matching acute angle, boom, they're identical. The other one is RHS, right angle, hypotenuse, side. Same idea. If they have a matching hypotenuse and one other matching side, they're clones. So RHA and RHS. You got it? Awesome. Let's get to it. All right, we're armed and ready. We've got our big clue from the isosceles triangle, that whole perpendicular bisector thing, and now we can finally find our first secret center. This one is all about the three corners of the triangle, the vertices. It's like a central station for them. This first secret point is called the circumcenter. Now just imagine drawing a circle around a triangle, but it has to be perfect. The edge of the circle has to touch all three corners of the triangle at the same time. Well, the circumcenter is the dead center of that circle. Think of it like a perfectly fitted bubble enclosing the triangle. So how in the world do we find the spot? This is where our clue from earlier pays off. You take one side of the triangle and you draw its perpendicular bisector. Remember, that's the line that cuts it in half at a perfect 90-degree angle. Then you just do it again for another side, and then for the third side. And here's the crazy part. All three of those lines will always cross at one single point. And that point, that's your circumcenter. So what's the big deal about the circumcenter? What makes it so special? Well, here's its superpower. The distance from that center point to each of the triangle's three corners is exactly the same. I mean, down to the micrometer. It has to be, right? Because they're all just the radius of that big circle we drew around it. That's its whole identity. Okay, quick pop quiz for you. This center isn't always in the same place. For a regular-looking acute triangle, it's somewhere inside. But what if you have a right triangle? You know, one with a perfect 90-degree corner? Where do you think that meeting point is going to show up? Take a guess. So it turns out the location actually depends on the kind of triangle you have. For an acute triangle, yep, it's inside. For an obtuse triangle, one with a big wide angle, the center is actually outside the triangle completely. Weird, right? And for a right triangle, it lands smack dab in the middle of the hypotenuse, that longest side. Super neat, super clean rule. Okay, one down, one to go. We found the outer center. But remember, I promised you two. So now let's hunt for the second secret center. This one isn't about the corners at all. It's all about the sides of the triangle. And finding it, well, it takes a totally different approach. Let me introduce you to the in-center. If the circumcenter was about a circle on the outside, the in-center is all about a circle on the inside. The biggest possible circle you can fit inside the triangle so that it's just kissing all three sides. Think of it like this. You're blowing up a balloon inside a triangular room, and you stop the second it touches all three walls. The very center of that balloon, that's the in-center. So how do we find this one? It's a different trick. Instead of cutting the sides in half, we're going to cut the angles in half. You draw a line that splits the angle in one corner perfectly. Then you do the same for the second corner and the third. And, you guessed it, it's the same kind of magic. All three of those lines meet at one single perfect point. That's our in-center. And what's the in-center's special power? Well, it's all about the sides. The shortest distance from the in-center to each of the three sides of the triangle is exactly the same. Those distances are the radii of that circle tucked inside. It stays perfectly equally distant from all three walls. Okay, we've got them both, the circumcenter and the in-center. They might sound kind of similar, but they are worlds apart. Let's put them head-to-head, a little showdown, just to make sure we've got this down cold. Let's break it down real simple. The circumcenter, that's for the big circle on the outside. You find it by splitting the sides. And its main thing, it's the same distance from all three corners. Now the in-center, that's for the little circle on the inside. You find it by splitting the angles, and its main thing, it's the same distance from all three sides. See? They're like perfect opposites. Look, if you walk away remembering just one thing today, let it be this. Circumcenter, equal distance to the vertices, the corners. In-center, equal distance to the sides, the walls. That's it. That's the whole ballgame right there. Vertices versus sides. So I'll leave you with this final little puzzle. Imagine you're designing a park, and it's shaped like a triangle. You want to build a big, beautiful, circular fountain, and the edge of the fountain has to touch all three corners of the park perfectly. Which secret center would you need to find to know exactly where to start digging? The circumcenter or the in-center? Give it some thought. Thanks for joining me on this hunt.